so to conclude this module, I just have one final set of observations to generalize what we have done so far. First question is, what if the medium was magnetic? That is, if mu was a function of space also. So remember what we did was, we took this first equation and what did we do to it?
Curl.
We took curl, right? So we did del cross E, okay, and that gave that basically said that j omega mu, sorry, del cross mu r h r, and that's a problem, right? Because I know del cross h, I don't know del cross mu h. So whatever process I did, I will not be able to follow it exactly in the same way. So what do you suggest we do in this problem?
Can you take mu r versus epsilon?
No, mu is in one equation, epsilon is in another equation. How do we absorb the two?
We separate out the magnetic and
How? These are coupled equations. How do we separate them out? The answer is actually much simpler. Just look at it.
Solve for mu h.
Mu is given to you. There is no need to solve for it.
You got mu r h as something h dash.
But I still don't know curl of that. I know only curl of h. I can't use the second equation. The second equation is the clue. I want to do whatever you do. I want to only take curl of h. So what should I do to the, should I straight away take the curl of the first equation or do something before that?
take mu to other side.
Take mu, supposing I take mu to the other side. So supposing I do 1 by mu r del cross E is equal to minus j omega h. Can I take a curl now on both sides? So I will get del cross 1 by mu r, okay, del cross E is equal to minus j omega del cross h, and then I can substitute over here. So by doing this, would I have eliminated h? Yes, right, because the next step itself I write minus j omega and I substitute over here j omega epsilon r E plus j. So I have got one equation in electric field which has all the given information about the problem. The given information is mu r and epsilon r. What is the price I have to pay? This is not a very pretty expression, right? It's curl of some funny looking object, and then we have to use the rules of vector calculus to open this up. So the price you pay is that the analytical formulation before I discretize and solve is a little bit more complicated, but it's nothing that we can't deal with. It's just more terms. Earlier this thing had simplified very nicely into only a minus del squared E, but now I will have many more terms. Okay, that's fine. So that's how we will deal with a magnetic medium. Now what we did was we took these equations. Let's assume that we don't have a magnetic medium. Let's assume that I have just mu naught. We formed an equation, the Helmholtz or the wave equation, only in E. Can I do the same thing in H? Can I form a del squared H term? I have one answer that says yes. Anyone else? So if I do, I have to do this, right? Del cross H. That's what I have to do. And since mu naught is just constant, then this would give me minus del squared H, because del dot H is equal to 0. But what do I have on the other side? I have a j omega curl of epsilon r E, right? Sorry, I wrote the whole thing again. Let's write this. So I have del cross H. So that's del cross j omega epsilon r E plus j r. Can I proceed with this? Do I know curl of epsilon E? So I cannot actually get a Helmholtz equation in H, because I don't know del cross epsilon E, I only know del cross E. So, I cannot simplify this. So, what would you do in this case? If you wanted to get an equation in H, what would you do? Same trick as this. So, what I will do is I will get a 1 by epsilon r over here and a del cross H, and then you will have a j by, that is okay. I don't need, I mean all I want is some way of simplifying del cross H. Now I can take the curl, I will eliminate E from this equation. I will get, so I am paying a price. Now I have a j by epsilon everywhere, fine. But those are the ways in which you will get around these problems if you wanted to solve if you wanted to get a Helmholtz equation in H. Okay. So, this is actually done a lot in the case of the photonic crystals community. If there is time later on in the course, we will have a look at it, but it is common. I am not just cooking these up. People in different parts of physics use these different formulations depending on what is convenient. So, that brings us to an end of this discussion on surface or boundary integral equations, where we started with the motivation of waves bending and found out this mathematical expression for Huygens principle. We used the extinction theorem to formulate the integral equations, then we just qualitatively discuss how to solve them, and we will look at further details in upcoming modules. Okay. So, the reference for this is this very nice book by Chu, and the book is Waves and Fields in Inhomogeneous Media, chapter 8. Right. So, any questions? Well, it is grungy. I know the definition of del cross any vector. I will have to calculate it, okay, if not analytically, numerically.
So we use the exception principle to take those two equations, right?
Yeah.
From there we apply boundary conditions.
Yeah.
So what about the Huygens principle?
Once we get these, once we solve these using, this is the extinction theorem, right?
Yeah.
We solve it, we get del phi, grad phi dot n hat and phi. Once we have got it, then we go back to Huygens principle and substitute it into this one. So, I know this now, I will get field anywhere. So, the two-step process. All right.